Good. All right, well, we'll get started. 9 o'clock here. Welcome, everybody. Thank you all for joining us this morning for our third part of Fueling the Future webinars, focusing on the hydrogen industry. Everywhere I go these days, it seems like everybody is talking about hydrogen, so lots of good interest in it. One of the things that we see not only in the hydrogen industry, but in many industries is that the processes continue to evolve and things are more and more challenging for valves and other components in that system. And unfortunately, maybe the valve industry hasn't kept up as quick or as it got the specifications. So we're definitely moving into some new territories here with hydrogen. And our goal at CGIS, obviously, our vision, world without valve problems, we're looking for abilities to solve those solutions for those more challenging applications. Today's webinar will be focusing on check valves, and happy to be joined here today with one of the industry experts on check valves, Tim Green from DSS Valves. Tim's been working with check valves for over 12 years now, and with DSS specifically for the last 3 years. Tim's got a BA of Science from the Air Force Academy and an MBA from Auburn University. And like I said, a very knowledgeable individual when it comes to all things check valves. Next slide, please, Tim. So again, definitely as we're heading into some new territories here with hydrogen and valving, we really encourage people to ask questions. This is a collaboration. I think our solutions are always are better when we can collaborate with our customers and end users. And these webinars are a great opportunity to ask your questions and have them answered, as well as share some of your feelings and your perspective. So the bottom of the Zoom call there, you'll find a Q&A button. If you want to ask those during the webinar, we will do our best to either answer them online or put into the slides. We'll interrupt and get Tim to answer those as we go. Next slide. I think that is probably all for me, and I will hand it over to Tim.
Thanks, Tim. All right, sounds good, Braden. Thanks for the intro, and thanks everyone for joining us today. We are here to talk about severe service check valves, and specifically as severe service check valves relate to the hydrogen industry. So before we jump right into that, I want to give a quick intro into DSS Valves for those of you that don't know who we are. DSS is now an 8-year-old company. But there's a lot more to the story than that. We're an 8-year-old company full of industry veterans who have spent careers making severe service valves. So we have several of our key employees that have come from multiple different manufacturers in the severe service valve industry and all came together. The company was founded in 2016. Primarily, flagship product line was a severe service knife gate valve. And for the last 3 years, we've been making severe service check valves. So DSS is located in Niles, Michigan. Show you the factory here. So this was the building that we built back in 2020. So during a time when the world was kind of shut down during COVID, DSS was growing, and we've continued to grow rapidly every year. What we do different than a lot of people is we are still a privately held engineered valve company during a time where a lot of companies are being bought up by corporate conglomerates and really being less responsive. We are focusing on customer requirements and focusing on making the best valves, doing it the best turnaround time for our customers. So the name DSS actually stands for Designed for Severe Service. So we do industrial valves. We do valves for the toughest applications. So we can do valves for general service, but that's really not where we shine. We are at the high end of valves. We are an engineered valve company, like I said, and we focus on corrosive applications, erosive applications, extreme pressures. So especially in this industry, we're seeing very high pressures, even at cryogenic low temperatures and extreme high temperatures as well. So DSS we're a global company now. We've got an install base of both of our key product lines, knife gates and check valves, across really any and all heavy industry. So this is just kind of showcasing some of the industries that we're in, the typical industries that you would expect. So jumping into hydrogen a little bit. So like Braden said, hydrogen is something that we are hearing about all the time now. So what's all the fuss about it? Well, as we all know, there's a global push, there's an international push to decarbonize, to make sure that that the world is seeing a cleaner environment. And one of the things that the international community has realized is that hydrogen can be used to reduce emissions in very hard to abate sectors. So some of the sectors that are most reliant on petroleum and on fossil fuels, so such as transportation, heating and power for buildings, heating and power for heavy industry, and then also industrial feedstocks. So for steel mills and for the space industry, hydrogen has a lot of uses these days. As you all know, though, hydrogen is not new. Hydrogen has been around for several decades, whether it's been in the refining space or in the space industry. Think back to the 60s in the space race. People have been using hydrogen for a lot, for many, many years. But the problem has been, it's been very segmented amongst different industries. There's been a lot of knowledge gained in different areas of the hydrogen industry. But what we're just now realizing is there's a need for harmonized standards to be used across production, transportation, storage, and even in testing using hydrogen. So what we're realizing is that there's a lot of startups out there. There's a lot of companies that have been around for a while that are getting into green hydrogen, blue hydrogen, gray hydrogen, and they employ extremely smart people. So we're working with chemists, we're working with PhDs, very smart people that know their process, but there's not a lot of information out there currently on what to do for piping and valves. So in a lot of cases, you guys, a lot of you on this call today are end users, are relying on companies like us, like CGIS and DSS, to be the experts in the industry and know all of the conglomerated information out there to be able to make recommendations for your processes. So I just wanted to list, kind of to show you, here's some of the standards that exist out there currently. You've got ASME standards, you've got NASA standards, there's ISO standards, there's SAND standards that most of us probably haven't heard of before. And then even going on from there, there's standards that have been around for a while. The last three on the list there, API 6D, MSS 410, the committee that produces the MSS SP standards, and then ISO 15848. These standards are ones that we know of and are involved in that are actively adding hydrogen to their standards to make sure that we're starting to see some of that combination of the information out there. So API 6D, we understand that there's a new hydrogen addendum that's actually going to be out hopefully by the end of this year is what we're being told. Then as far as MSS Committee 410, so they are currently working on, and DSS is actively involved in this committee. So we just sent a couple of employees last week. They're actively creating a testing standard for hydrogen. So it's going to contain test criteria for gaseous and liquid hydrogen. And then the plan is to be able to get that out there as soon as possible, get it submitted to ANSI for approval as an ANSI standard. And then ISO 15848, a lot of you are familiar with that as a helium test, fugitive emissions test for valves. And the committee, the ISO committee, is actually meeting and with a goal of releasing new hydrogen test criteria by either late 2024, possibly rolling into 2025. So a lot of good activity out there. We're involved as much as we can on a lot of these boards and committees to be able to be as knowledgeable as possible about it. So hydrogen, it's very, very challenging. So just wanted to go through some of the challenges that we see that apply to piping, valves, and just the hydrogen industry in general. So one of the biggest things that we see is the potential for leakage. So as everyone knows, if you look at a periodic table of elements, hydrogen is top left. So it's the very smallest atomic mass of all the elements, which means it's very, very tiny. And so a very small molecule such as hydrogen is prone to leakage. It's very hard to contain something as small as hydrogen. So what's the big deal with leakage? The problem is, hydrogen leaking out to the atmosphere on its own is probably not going to get anyone upset. The US EPA, the regulation bodies aren't, as of right now, regulating the leakage of hydrogen because there's already hydrogen in the atmosphere. The issue comes into play with the flammability. So hydrogen is one of the most flammable fuels out there that exists. So it's extremely flammable in concentrations from 4% up to 75% mixture with air. So very, very flammable. And then also once it catches on fire in daylight, in a very bright sunny day, it's an invisible flame or nearly invisible. So if you've got a facility that's got a hydrogen fire, it's very hard to detect that that's even going on. And so very, very crucial to make sure that you don't have flammable media such as hydrogen leaking to atmosphere that could cause operator safety issues, or just the general unsafe conditions that would exist with a fire in situations like that. So another big challenge that we see, and a lot of the questions in the hydrogen space right now are surrounding the materials that are used for the piping and for the valves. So two of the failure mechanisms that we are familiar with are high temperature hydrogen attack, which forms with methane under higher pressures and temperatures, which leads to material failures. So that's one of the concerns. Also, hydrogen embrittlement is another concern. So hydrogen is known to react with specific materials and also cause failures, can form cracks, makes the material brittle, and especially in high pressure environments is very dangerous. So one of the things that we've learned is that there's several materials that have been out there for a while, but 300 series stainless steels, austenitic stainless steels, are some of the most effective materials to be used with hydrogen. So like I said, in the refining space, 347H, that's been out there for a long time now for high temperature hydrogen applications. Another one, 321 stainless steel. And then also what most people think of when they hear stainless, when we're talking valves, 316 stainless steel. Starting to see some requests coming from the end users to us was specific to very specific chemistry requirements. So minimum nickel contents, as you know, stainless steels are really made up of three main components: chrome, nickel, molybdenum. Well, we found that the nickel content is very crucial. So there's customers that have specific minimum nickel contents that are being requested. Somewhere in the 12% range is what we're seeing. And then also lessons learned. We found that materials typically with a Rockwell hardness below 32 are not prone to hydrogen embrittlement. So a lot of things that we've learned through experience, through discussions with other peers in the industry, through end users. And then also this runs the price up quite a bit, but we've also found success using the high nickel alloys such as Hastelloy, Monel, and Inconel 625. Those are good materials to use as well. Quite a bit more expensive than austenitic stainless steel, but if you're talking about wanting to designed to work and to not have issues, that's some good materials to consider as well. And then something, I'll be the first to admit, chemistry. So I wanted to add this to it because like I said, we're working with some very smart people in this hydrogen space. And what we realize is that as we're out there gaining information through attending VMA meetings, through attending MSS, through different publications that are available, it takes nearly a college understanding of chemistry to be able to understand this hydrogen industry and a lot of the processes that are taking place with the water electrolysis and the steam methane reforming. And there's a lot of information out there that that can be intimidating when you're trying to wrap your head around what's going on in the industry and what do we need to have to offer. So it's very crucial for us because we're the valve experts. We know how to make severe service valves. We know the materials. We're able to provide these valves in very specific engineered formats. Very crucial for us to be in communication with the end users, with the people that understand the chemistry, probably better than we do as valve manufacturers, to be able to make sure this is a collaborative approach. So let's move on a little bit into DSS and why. So mentioned to you, we do severe service knife gate valves. We do severe service check valves. Today, we're going to focus specifically on the severe service check valve because there's a lot more broad use of check valves in this space, especially when you're talking about the pressures and the gases and such that we're dealing with. So what we know is that there's not a lot of thought that goes into check valves across all process industries. Check valves are typically sold as a low-cost product. They don't add a lot of value to the system in most cases. They're sold typically by the pound. But what we know is there are some very critical applications across all of the hydrogen space, whether it's upstream where the hydrogen is being produced, midstream where it's being transported, or even downstream at the end use. There are check valves throughout every portion of this of those processes. And our experience in this space has shown that there are plenty of applications, and most applications, I would say, where traditional commoditized check valves just don't cut it. They don't work for these applications. So what we know is we need to be able to produce a valve for you guys, for this industry, that can handle the high pressures. And it needs to be able to handle the high pressures without any leakage at very high temperatures, very low temperatures. It needs to be able to work all the way from cryogenic up through as high as the ASME standards will allow these to go. And it needs to do that while doing really two things. A check valve it's a dumb product by nature. There's no actuator. It's operated by the flow. So it needs to do two things. Primary function, prevent non-return, or non-return valve in some cases is what check valves are called. So we need to make sure that the check valve opens in one direction and it closes in the other direction, preventing backflow, prevents processes from mixing back into themselves, protects pumps, protects compressors. Very crucial that a check valve prevents backflow. The other thing that's very crucial is prevention of fugitive emissions. So both of these things went into the design of the DSS severe service check valve. So this next slide just shows a DSS. This is a 6-inch class 300 severe service wafer check valve disassembled. One of the first things you'll notice about our valves is there aren't many pieces. So in a lot of cases, in most cases, when you're talking reliability, less pieces means less pieces to tear up. So if you take away one thing from our presentation about severe service check valves today, it's this component on the right. This is probably the most important piece that makes this valve better than most check valves out there, is that it's a single piece. Disc, shaft, hinge pin is all one integral component. The disc fits into the seat insert. So the seat is actually machined integral to this seat insert, and it fits down into this mill slot. And then the body is actually pressed over the top of the seat insert. So the disc fits down into here, body is pressed over the top of it. And next slide shows you what an assembled severe service wafer check valve looks like. So a lot of words on this slide. We'll go through each and every one of these design characteristics here in future slides, but just showing you what an overall view of the DSS severe service check valve looks like. So this is a cutaway view of the same valve. And you'll notice here, this is a soft-seated version. We can do them, and there's a lot of conversations to be had about elastomers and whether they should be used in hydrogen, whether they shouldn't be. Just know we can do it with a soft seal. We can do it without a soft seal. We can do it with very highly machined metal-to-metal seat. But just this so happens to be a soft-seated version. So you'll notice here in this cutaway that the DSS valve has a counter bore on this upstream side. And when this valve is pressed together on a hydraulic press, everything goes over the top of this seat insert. So when you're talking preventing fugitive emissions, you need to make sure you've got redundancies in place to ensure that these valves don't leak to atmosphere. And we do that through an interference metal-to-metal fit. So this seat insert is actually slightly larger than the ID of this counter bore. And then also on the outside of that, optionally, in most cases, we will put an O-ring on here as well too. It's an assembly O-ring. You'll see it listed in our parts as an assembly O-ring because it serves the purpose to help align the components when they're pressed together on a hydraulic press. But it does have some backup sealing functions. If that's a huge sticking point for your process, we can get rid of it altogether. We've got fire tests to prove that the metal-to-metal interference fit is good enough. But in most cases, we put that backup seal on there. And then the third redundancy is we make sure we maintain minimum wall thickness per API standards in this location as well. And what that means is in most sizes that this seam lands right on the raised face on the upstream side. So you've got a third redundancy being the flange gasket actually covers up the only potential leakage path. Then you've got the backup seal and the metal-to-metal interference fit. So this is show a little animation of how it's pressed together, but these valves are pressed together on a hydraulic press. Very simple assembly. You just have to line it up, push it together. They're also easily repairable. If you ever needed to put new trim in these valves, they can be pressed apart just like they're pressed together, but in the opposite direction. Let me move on here to the next slide. So what we do different than most check valve manufacturers out there too is that we start with the highest quality raw materials on the market. So especially with a lot of the hydrogen that we're seeing right now. It's smaller bore stuff, usually 8-inch and below. We prefer to make these valves out of wrought material, meaning bar stock, forgings, plate. We can use centrifugal castings, but we prefer to make these out of wrought materials because it allows us to keep very close watch on the chemistry requirement. We get these from domestic sources. And there's also some benefits when you're talking wrought materials in cryogenics. One of the concerns that we've seen in my past, I've actually personally done some cryogenic tests, and stainless steel, when you say 316 stainless, if you get it in the cast form, it's actually not fully austenitic. In some cases, a cast version of stainless steel can have some ferrite content in the grain structure, which actually can lead to issues with the valve down at extreme low temperatures. So to prevent that and to prevent the need for additional impact testing of the material, it's easier just to use wrought material. It's well set up for our processes because every single component of our valves, whether it's the seat insert, the disc, the body, they're all CNC machined. So every single surface is a CNC, highly nice surface finish on a CNC mill or lathe. And then as expected, our valves, our whole shop, our entire company is ISO 9001 certified. So we maintain traceability from the steel mill where the material is produced all the way through the end product. So just kind of going over an overview of what we offer. We can go all the way up to 54 inches. We would probably go larger if given the opportunity, but for purposes of today, most of what we're seeing is smaller bore, higher pressure class type stuff. Face-to-face dimensions, our valves, our most economical offering is API 594 wafer. That's the standard takeout that you would see with a dual plate wafer check valve. Ours being a single plate swing type wafer check valve meets the same face-to-face though. So drop-in replacement for those style of valves. But we can also do these with ASME B1610 face-to-face. So we can do a fully flanged version that meets the takeout of a flange check valve, or we can do non-standard. We can do thin wafers. Again, these are 100% machine engineered product that we control all dimensions. Nothing's coming into us precast. So we can do industry standards or we can go non-standard if required. Flange accommodation, some of the requirements we're starting to see for the hydrogen space, people are wanting to get rid of flanges altogether because of the potential for leakage at the gaskets. So we're starting to see hub end requests. We're starting to see butt welding requests. We can do all those. And anything that's required, gray lock, blue sky, any of those type of hub ends, we can do it. And we can also do the valves with butt welding ends. Each valve's marked per standard MSS requirements. They're all hydrostatic tested. So every valve gets a hydrostatic test before it leaves the factory. But also because of the temperature range, like I mentioned, we can do cryogenic testing all the way up through any kind of high temperature testing that's required as well too. We do class 150, ASME class 150 up through class 4500. And then also we can get into the API 6A pressure classes all the way up to 15,000. Standard body styles, wafer, lug wafer, flanged, again, specials upon request. And then materials, if you can buy the material and machine it, we can make a check valve out of it. So most of what we're seeing, again, kind of goes back to, in this space, the 300 series austenitic stainless steels. But if there's something else that your plant or your customer is using, we can certainly source it and make a check valve out of it. And then again, we offer these in metal seats or soft seats. So I want to talk a little bit about failures that we see and a reason to use this style of valve in your processes in your hydrogen industry to make sure that you're getting a high quality product that works. One of the primary failure mechanisms that we see with check valves across all industries is the disc breakage. So on the right here, I've got a couple of photos. This is a traditional dual plate API 594 wafer check valve. The discs on these valves, if you'll notice, there's 6 or 7 different pieces. There's spacers in here between all the parts and the hinges and the hinge pin and the springs, very prone to breakage going downstream. So you lose your disc in your check valve. Now you don't have a check valve. You have a spool piece potentially. So it's just going to allow free flow in both directions, which could be catastrophic to other equipment or even operator safety. And then again, the other style of valve that's probably second most common we see across all industries is a swing check valve, bolted bonnet swing check. This is the view down the bore of a 16-inch that I saw at a plant where the disc, it was still in the valve. It wasn't large. I mean, it's too large to travel downstream, but the hinge pin broke and the disc's just now sitting down into the bore of the valve. So our single piece disc replaces 6 or 7 different components that are prone to breaking on these style of valves. The hinge is integral with it. There's no welding in this location, very strong component. So these valves are designed to give years and years of repeatable function without fail. This is showing one. This is a 16-inch stainless steel disc being 3D milled out of a solid piece of stainless steel plate. So again, no welding. This is probably the most critical location. We put a nice radius on all of them here for added strength, and no welding, all one solid integral piece. Going back to the fugitive emissions discussion that we were having. So this is an upstream view of what our check valve looks like. So you can see the redundancies I mentioned to you. Because we maintain wall thickness, this seam lands right on the raised face gasket surface, again, covered by the gasket. And then you've got the interference fit. We put a lot of thought into that. And then the backup O-ring, if allowable in this industry, into your plants, put the backup O-ring on there as well. So I've got some photos here showing this is what a traditional wafer check looks like. On top and bottom, they've got these threaded plugs. It's just a pipe plug with Teflon tape. And if anyone's got experience in the manufacturing industry, one of the hardest processes to repeat is threading and tapping. A lot of machine shops will use their taps until they're out of tolerance. And what that leads to is a pipe plug that doesn't form a very good seal with the actual pipe tap in the body. So they put Teflon tape around the plug, put it in, and that's all that's preventing some of these valves from leaking harsh chemicals, flammable chemicals to atmosphere. Okay, another problem, probably one of the more common reasons that check valves fail across all industries too, is the issue of slamming due to improper sizing. So check valves are not typically thought of as being the most smart product out there, not the most, not a lot of thought goes into sizing. Typically, people put in a check valve based on the line size. So if they have an 8-inch valve, they put in an 8-inch bore. And a lot of times, because the disc requires a certain amount of velocity to keep the disc fully open and stable, a lot of times there's not enough velocity to keep it open, and you see slamming. So DSS has the capability to run CFD calculations and different sizing calculations to determine if the valve's seeing enough velocity to remain fully open. And if not, we can actually reduce the bore on our valve. So it's not uncommon to see a DSS valve with a reduced bore, which seems counterintuitive. You're blocking the flow area. You would think you're introducing more pressure drop, but a check valve that's slamming in service flows a lot better than, or sorry, a check valve that's slamming in service flows a lot worse. It actually is not even achieving its published CV than a valve that has got a smaller bore with a fully open and stable disc. That's going to provide much better flow, much better service. So
sorry to interrupt you. There's a question that came in that I think is probably relevant to this slide. Is this how do the valves perform in reciprocating compressor service?
Reciprocating compressor service is one of 2 places we always recommend not using our style of valve. So that's one of those where we just gracefully bow out and say there are other style of valves that have got, you know, there's some trade-offs there, but there are other style of check valves that do better in reciprocating service. Because you have the potential for the disc to just open and close all day. So the 2 cases are reciprocating service and vertical downflow are the places we don't recommend putting ours. So just that would be one of those we would just have to, like I said, just bow out and, you know, let them look at other avenues.
Perfect. Thanks.
Yep. So I talked a little bit about check valve sizing. So check valves rely on Bernoulli's theorem for the disc to remain fully open and stable. And what that means is, for those of you that are probably aware from your school days, is Bernoulli's theorem states that when you've got a flow, so you've got flow through a pipe, when a constriction is introduced, so when you reduce the cross-sectional area of the pipe, you get a increase in velocity going through that cross-sectional area that's reduced, which results in a pressure drop. So it's just like, to dumb it down, this is a photo from several years ago, but my son trying to squirt his sister with a water hose. It's the same principle. As you're blocking some of that flow area, the water speeds up, goes around your thumb, and travels further. So it's the same principle when you're thinking about sizing a check valve, because again, we don't have an actuator. We're one of the only styles of valves that's just operated by the flow. We rely on a velocity to keep that disc fully open. And so what we know is that each style of check valve, I've got them listed down here, has a minimum required velocity to remain fully open and stable. So for different styles of valves out there, some of them have quite a bit higher velocity than ours, but we've done flow calculations to prove ours takes, depending on the size, between 6 and 7 feet per second of water to be fully open and stable. And you can derive this for any and all medias. It's reliant on the specific volume of the media. So for water, it's around 6.2 feet per second. So we know what velocity is required to keep the disc fully open. The next piece of the puzzle is when you're sizing a check valve, you need to know what velocity the check valve is actually seeing. So standard formula for determining mean velocity of flow in the pipeline. And so I won't drag everyone through a math calculation here, but basically what the gist here is that you run a calculation. In this case, we know our valve takes 6.2 feet per second to remain fully open and stable. We look at the mean velocity in the pipeline in this case, and it's only 4 feet per second, around 4 feet per second. And when the velocity is below our min velocity, we have to assume that the disc is slamming or fluttering in service. So in this case, we realized that an 8-inch bore would be too large. Now we go down to a 6-inch bore, and that elevates the velocity through Bernoulli's theorem up to 7.22 feet per second. Now we're above the minimum required. We know now that's a good fit. So in this case, we would sell an 8-inch valve with 6-inch internals. Because these are all CNC machines specifically made to order, we can make a valve that still fits 8-inch flanges but has a 6-inch internal inside of it. Another issue that we solve in the industry is pressure drop. So when we got into the check valve industry at DSS 3 years ago, we realized in looking at all of our competitors, or just about all of our competitors' brochures on the market, there's a lot of bad information when it relates to published CVs. So what we realized, there's several different dual plate wafer check valve manufacturers out there on the market that produce this style of valve. And they all publish higher CVs by quite a bit. In some cases, over 2 times the CV that we publish for our nearly unobstructed bore check valve. And we weren't okay with that because it didn't make any sense. You can look at these style of valves and tell they don't flow as well as ours. So we actually sent 9 valves, ours along with several of our competitors, up to a flow loop and did some real world testing to prove DSS has one of the best flowing check valves on the market. We're just not willing to lie about the CV. So we will publish our CVs that we proved using CFD and real world flow analysis, and we'll defend that all day long against these valves. I mean, you can tell this one here was installed in a phosphate mine. This is I think it was a 30-inch dual plate. And you can see just over time being that obstructed leads to this scale buildup, which plugs the valve completely up. So DSS spent a lot of time engineering a tapered inlet to our Venturi inlet to make sure that these valves flow better than all of the other check valves on the market. And then, like I mentioned to you, DSS is located in the US, and our supply chain is all US based as well too. So we focus on quick deliveries. We're able to bring in raw material, get stuff machined quickly. And then we keep quite a bit of inventory on our shelves. So DSS has, at all times, we keep component parts on the shelf. We don't keep completed valves because, sorry, I'm getting a little bit of a lag here. Stop. There we go. Okay, so as you can see, we keep bodies, seat inserts, disc. There's too many permutations of the materials and body styles for us to keep completed valves, but we keep component parts on the shelf where we can pull parts, assemble, test, and ship in a very, very quick turnaround time. Each and every DSS valve is tested per API 598. So before they leave the factory, we press them together on this hydraulic press, and then we also hook up the hoses and perform a hydrostatic shell and seat test per API 598. If you require any ultrasonic, mag particle, liquid penetrant, PMI examination, we can offer all of that as well too. And because we're ISO 9001, we maintain traceability throughout. We can provide a certificate of compliance, MTRs, NACE certification, a full birth certificate of our valve going all the way back, traceability all the way back to the steel mills. So I want to talk a little bit about testing. So this is going to be one of the very important things as it relates to the hydrogen industry, is making sure that we are performing tests that are adequate for valves to function in hydrogen service. So this is just showing the chart I've got up here. This is the closure test requirements of API 594. And you'll notice right away that check valves, they always have their own leakage requirements as compared to other style of valves. So check valves and other valves except check valves. So the main reason for that is because, again, check valves are operated by the flow. They require backflow to help seat the disc. So check valves, you'll notice with water, are allowed to leak 3 cc's per minute per valve inch, which is, it's a pretty slow drip rate of water. But if you were to extrapolate that out into a leakage rate for hydrogen, you start to see that's probably going to be a fairly large leakage rate. So we've never felt like this was okay for a valve to leak 3 cc's per minute per inch with water. So DSS has always strived to make sure our valves seal much, much tighter than the industry requirements of API 598. So we're able to actually, because we CNC machine the seats on our disc, on our seat insert, we can actually get these valves to pass hydrostatic tests in a lot of cases with 0 drops. So very, very tight shutoff as compared to most check valves out there. It's kind of counterintuitive too, but some of the hardest tests for check valves is a class 150 gas test, because check valves, they seal tighter as the back pressure increases. So if you're only at 1.5 times the working pressure on a class 150 valve, you don't have very much back pressure helping to seat the valve. So you have to have a very, very flat surface to be able to make sure that these valves seal tight. So DSS has spent a lot of time making sure that we have very, very tight tolerances and that our valves are capable of sealing across the seat much, much greater than industry requirements. But I want to talk to, as it goes, kind of going into cryogenic testing. So as I said earlier, I've done several cryogenic tests myself, testing severe service check valves all the way up to class 1500 with helium as the test media. And what I've seen in the past, and what we need to all be careful of, is because check valves are harder to get to seal than other style of valves, we need to make sure, as we're writing specifications, as we're quoting projects, that we're not writing ourselves into a corner on making seat leakage requirements that aren't achievable by check valves. Because what we know is that with a check valve, if you want 0 leakage across the seat, repeatable every time, you need to use an elastomer seal. You need to go with a soft seal. Because with a metal-to-metal seat, even if it passes in the factory 0 leakage, once one hair gets on the seat or 1 grain of sand, all bets are off. So soft seals are the way to go. But when you're talking cryogenics, now you're at temperatures that are lower than the ratings of a lot of the elastomers. So we're starting to see a lot of end users, they instantly, their mind goes to PTFE. Okay, fine. If elastomer doesn't work, go with a reinforced PTFE or a virgin PTFE seat. Now you're good. It's a soft seal. But it's important to note that a lot of manufacturers in the check valve market will only certify their soft seated, their PTFE seated. I need to clarify, not all soft seated. They will only certify their PTFE seated check valves to metal seat leakage requirements, because PTFE is actually pretty hard to get a very tight seal with a check valve, because again, we're relying on whatever back pressure is there. And if the O-ring you're using is not perfectly flat and you've got a molecule as small as hydrogen or helium, becomes a very, very tough test to pass. So we just need to be cognizant that we're not writing ourselves into any corners and requiring things that just aren't possible by manufacturers. But just know at the same time, we're an engineer valve company, and we will work with you to meet requirements that are achievable, and we can ensure we've got the best leakage rates of any check valve manufacturer on the market. So Cryogenic testing standards, two of the most common ones out there that everyone's probably familiar with are BS 6364. That one's been around for a long time. MSS SP 134. We can test other requirements, but those are two of the most common ones that we see. Some of the weaknesses, though, that we're seeing, potential weaknesses, more of a question than anything at this point, but the current cryogenic testing standards that exist are written around using liquid nitrogen as a cooling media and using helium as a test media. And so the issue arises that liquid nitrogen is negative 196 degrees Celsius, while liquid hydrogen is negative 253 degrees Celsius. So the question is this good enough? Well, if you look back at what some companies or some organizations such as NASA has been doing going back to the 60s, they built all their hydrogen piping for their test stands, for their launch pads in the 60s, and that's what they used. At least that's our understanding is what they used, and it seems to have worked well enough for them for this amount of time. Is that enough to say, a few anecdotes here and there that it's good enough? I think the question mark is still there because we need to all be sure, is it good enough or is there something we need to do differently? And that's what the MSS committee is currently looking at. So again, same thing, you got the temperature difference, and you got the medium, the actual test media between using helium and hydrogen. So yes, hydrogen has the smallest atomic mass, but helium actually has a pretty small radius. It's a very small molecule, and it's in some cases it's actually smaller because it's a more dense molecule than hydrogen. So again, it's probably been good enough in a lot of cases, but MSS and others are looking at is it worth adding hydrogen as a test media to make sure we're actually testing these valves using the same media that they're going to be used in service. Some of the considerations, though, are safety. So is it safe to use a highly flammable test media? I mean, it's even when you're talking about helium as a test media, standing next to a class 1500 valve after it's been taken out of a cryogenic tank and sniffing around it with a mass spectrometer, that's a pretty nerve-wracking test on its own. So add in the added element of a flammable media. These are just some things that we're having to think about right now that we're going through with these committees in the industry to make sure that we're all looking at all of the different aspects of this. So moving on from there, I want to talk about, so we've also done fire testing. So DSS has passed API 6FA fire testing. And this was an important test for our design because it proves that the seat insert, even once this O-ring has gone away, still passes helium leakage tests. So it proves out the design that the metal-to-metal interference fit is good enough to make sure that this valve can withstand exposure to an 1800-degree fire. All elastomers have melted away, and it still prevents fugitive emissions. And then ISO 15848, we were also able to pass that test with flying colors on our first try as well, too. So as the standard is updated, if they add hydrogen as a test medium, we will certainly stay up to date and make sure that we are qualifying using all the tests that our end users and our customers require of us. All right, and then I just want to touch on a few different options, things that we can do with our valves to make sure that you know exactly what we have to offer. So one of the things is the internal spring assist. I mentioned to you that's an optional component. So API 594, the wafer check valve standard, shows a spring in the drawing. And so in most cases, people ask for it. They're just used to seeing it in there. In a lot of cases, though, if water hammer is not a concern, it's best to just go ahead and get rid of the spring altogether because it's just one more moving part that has the potential to fail. I mean, it's the weakest link on an otherwise very robust valve. So a lot of times what customers will do is get rid of the spring altogether and use our tilted seat. So you can see in this image here, the seat is actually machined on an angle, and that allows you to put the valve in a horizontal flow orientation, and it allows the downward force of gravity to pull the disc positively back into the seat and provide shutoff. So get rid of the spring, use a tilted seat. You've also reduced the cracking pressure. So the cracking pressure on these is extremely low. It's less than 1/4 of a PSI. So they open under very low pressure, they close, they don't have as far to swing. It's just a really good design element that leads to a very robust valve that can last for a long time. And then we can actually beef up the disc of our valve as well too. So if you've got applications where you're concerned about the disc going from closed to fully open, we can actually put these stops, these internal integral stops on the backside of the disc. And that's just extra sacrificial material that helps the disc as it opens, protect it from damaging itself when it opens into the body. So DSS, Severe Service Valve Custom Engineering Company, we can make these valves look a lot of different ways. So we've got our standard off the shelf, more industry standard like the API 594 wafer check. But when we're getting into these real exotic applications, we can make these valves look just about any way we want. So this would be an example here of a hub-ended version with blue sky hub ends, valves fully. It can be removed easily from the line using these hub connections. If we were to make this with butt weld end connections, all we would do is machine this down and just put your standard butt weld connections on there. And then also we can put standard ASME or DIN flanges on these as well. This is a combo unit, so we haven't talked a lot about the knife gate today because a lot of what we're seeing right now is more check valve related. There's check valves across pretty much all aspects of the industry. But we do have some customers now that are coming to us for knife gates. When you're talking about decarbonizing, when you're getting the carbon out, you've got to do something with the carbon. And a lot of times that leads to solids in your process. So we've got customers actually in the hydrogen space that are using our knife gates, our severe service guided shear gate valves to isolate against carbon as well too. So one thing that we can do, this is what the knife gate valve looks like, but we can actually pair it with a check valve if you need non-return function and isolation. And this valve right here fits in the same takeout as a gate valve or a ball valve. We can actually custom make the end-to-end dimensions to make it fit in existing takeouts of other style of valves. And then also when we're talking midstream applications, if you've got lines that need to be pigged, we can make a full flow, full bore check valve per API 6D, and the disc gets fully out of the flow path, allows you to pig the line and make sure that the disc is open wide enough or full enough for it to meet API 6D minimum bore requirements. So that's all I've got for the DSS presentation. We've obviously would like to open up the floor to questions. I did want to make sure that we acknowledge that there's a lot of information out there, that we've attended a lot of summits, we've attended a lot of meetings, we've even watched the other webinars CGIS has put on and collaborated with other manufacturers. So just wanted to make sure we give thanks to the companies that have been willing to share a lot of their information about this space, because again, we're all learning about it together, and we want to make sure that the goal here is to improve the industry. So with that in mind, that's our goal. So I'd like to open it up at this point if we've got any questions.
Yeah, perfect. So there's a couple coming in right now, Tim. I'm sure there's going to be more. So first one is API 6 FA is a fire test certificate for safety in hazardous applications. Is that correct?
Yes, it is. And it's typically been a standard that's required in the oil and gas industry. And that just proves that your valve can go in, it can withstand a fire, and it's not going to leak the atmosphere. It's going to still seal after being exposed to a fire in a refinery type situation. But it would also apply to a hydrogen plant or any other place where you need to make sure your valve can withstand a fire. We've talked a lot about too, this is our wafer style valve, but a lot of customers prefer, when we're talking fire safety, to use a lug wafer. So same face to face, but we would actually use bolt pattern with actually through or threaded bolt holes. And that gives extra fire protection because it now protects your studs or your bolts from the potential of fire.
Gotcha. All right, perfect. Another question is about CRNs, and yes, every DSS, both knife gate and check valve, are fully CRN'd, and yeah, and that's for special designs or special materials and stuff as well, I assume.
Yeah, well, it's for we submit our brochure, which has basically all of these materials that we've talked about in it. So if there was anything non-standard, obviously we've got the ability to. We were talking this week with a customer about a steam jacket. Well, that was something that didn't fall under our certification, but we can add it if we need to. So we're agile. We're willing to talk and add different certifications if it is a requirement for certain customers.
Right. Okay, perfect. But for the most part, we're covered. Next question is about small sizes. So that's definitely something we're seeing in hydrogen space, especially around some of the pilot plants, is smaller sizes. Where do we start with this design? Where are we limited?
We start with NPS, nominal pipe size 1 inch. So once you get smaller than that, it gets pretty tough for the CNC machines that we have. So nominal pipe size 1 inch is where we start.
Okay. And pressure range, I think you'd mentioned class 4000, but and that, is that right? Or you can go up to.
Well, we can do API 6A, which is the wellhead standard, and Christmas tree standard has it goes all the way up to 20,000. We right now state 15,000, but there's really not a limitation. I mean, as long as, because we've had customers ask us for things for space industry that are outside of any industry standards. So there's no limitation on the wall thickness that we can use. We can buy whatever dimension materials we need. So, but it states in our brochure, class 4,500 for ASME or up to API 6A class 15,000.
Okay, perfect. Yeah, I think one customer has that, or one the attendees here is asking about up to 900 bar, which is I think 1350-ish psi. So yeah, should be within range.
Yep.
All right, perfect. What's the difference between API 6 FA and API 607 power safe?
My understanding is 607 is for actuated valves, I believe. So we looked into it and it didn't apply. So we did 6FA, and 6FA used to not even have check valves. So 6FD used to be the check valve standard, but they've rolled it all into one now. So that's just what we decided to go with. But again, something else needed of us, we'll be happy to run additional tests if there's a market for it.
Yeah, I think 607 is quarter turn valves. And 6FA is specifically for valves with metal seating on there. Okay, sorry, lost my space here. You talked about the tilt seat design. Why wouldn't you always go with the tilt seat design? Is there any disadvantage to going with the tilt seat design over?
There's not really a disadvantage. You could use the tilt seat with every single valve, even if you use a spring. It just adds extra cost. Gotcha. So it costs. We do these all on 3D mills. So when you're talking about putting that extra dimension on there, it just runs the price up a little bit on the machining. There's no reason you couldn't use the tilt seat on every one. Now the spring is if you've got water hammer as a concern. So hammer being the reverse flow, causing that disc to slam close and create a shock wave in the line. That's when a spring really helps, is to get the disc closed rapidly and prevent hammer. But if that's not a concern and you want a valve that opens very easily under very low velocity, we talked about sizing. So when we're 6 to 7 feet per second of water with a spring, if you get rid of the spring, it cuts that in half. So it's around 3 feet per second. So it allows the valve to open easier as well too. So unless water hammer is a concern, I would just recommend in a lot of cases get rid of the spring.
Gotcha. You talked about cryogenic, but we're also seeing some high temperature applications coming out of this industry. Any limitations, or where have you seen, or where are we limited to?
No, I mean, with our design, because we're not relying on the elastomers, there's no limitations. So as long as we're within the pressure temperature ratings of ASME B16.34, there's not any reason that we can't go up to the full max allowable.
Sounds good. Just a couple more here. When it comes to embrittlement, is material selection the only thing to prevent it, or can coatings play a role in protecting the valve?
Definitely. Well, obviously, for the sake of time, I glossed over a few things, but so material selection is primary because you want to make sure you got a good base material, but there are definitely coatings, and also surface finish has to do with it as well too. So making sure that you're machining and different manufacturers have different surface finishes, but a nice polished surface is going to do better than a rough as cast type finish. So surface finish and definitely coatings. So there are other manufacturers out there that have proprietary coatings. There's other companies that offer coatings that we can do. And that's one of the things we're investigating right now with our engineering department is what coatings do we want to be able to offer? Because in some cases, you can actually make a carbon steel act like stainless steel if you've got it coated correctly. So,
right. And then you talked about the standards for hydrogen. Is there one that you're look at, you think is going to be more useful for valves and check valves over another, or is it a combination?
probably a combination. Obviously,
Yeah.
6D applies. I mean, we use a lot of 6D when it comes to check valve design, testing, and such. And then also the MSS one, I think is going to be very helpful because that's going to lay out the testing criteria. And MSS is meeting, my understanding, I'm not personally on the committee, but two of our key employees, like I said, were there a couple of weeks ago. And they've got some really smart people, some good industry experts that they're consulting with to make sure we do it the right way. So I think that test standard is going to be very good.
Perfect. Awesome. I think that's all the questions. Oh, there's one more. Is there no hydrogen code requirement to use fire safe valves? Is your recommendation. So do you know with that MSS committee, are they looking at requiring fire safe valves, or is that
I would
still
have
too
to
early to
I
say?
would have to ask on that one. I don't know. From what I've been told, I think they're focusing specifically kind of narrowly on the test requirements of of running a hydrogen test, but I'm not sure. I can certainly find out.
Yeah, I know. I know in the past looking at some other applications like ammonia, same sort of precautionary needs of fire safety. There's standards that contradict each other. I know some of the UL codes, valves that meet the UL codes for ammonia don't necessarily are fire safe, and that industry fire safe valves are often recommended. So definitely more research is needed in that front. But yeah, based on the flammability of hydrogen, I think we'll probably see more and more of that fire safe code required.
One of the good things about this design, though, specifically, is a lot of the concerns that come up with the fire testing, the hydrogen testing, helium testing, is we don't have the packing systems, we don't have the glands, we don't have the actuation, we don't have all the stuffing boxes, we don't have all of the stuff that is the problems with a lot of the actuated valves. It's a very simple design that's pressed together using very engineered interference fit, using ISO standards to make sure that we've eliminated the possibility for a lot of those leakage points.
Right. Yeah. It's just almost inherently fire safe by the design of it. Yeah. Perfect. Good question that came up just now too. There no mention of cleanliness or for shipping or sort of cleaning requirements. We've seen oxygen. Is that something that's being discussed?
Yes, definitely. So we've got the ability to ensure these valves are clean per oxygen requirements. You've obviously got NASA has got their cleanliness standards that talk about different particle sizes that are allowable. But yeah, the cleaner the better when it comes to hydrogen service, because very, very small amount of debris can become a big issue. So yeah, definitely. And it's a lot of times right now it's customer requirements coming in. It's whatever's being asked for, but we can certainly comply with any cleaning requirements that are brought to us. And we don't have a clean room currently at DSS. So what we have third-party companies, a lot of the companies are the same ones that have, presented at VMA about some of these. So third-party companies that we can partner with to do any kind of cleaning required.
And CGS does as well. One in Edmonton and one in Quebec, so we can do any of that cleaning stuff. Yeah. So this is a follow-up question. Any codes for hydrogen valve cleaning? I haven't personally seen any. I imagine in maybe some of the NASA specs there would be, but do you know off the top of your head if there's any?
Most of what I've seen is oxygen cleaning.
Yeah,
because it's more related to making sure that the petroleum products and everything is out of it, so you don't have a fire in the pipeline. That's kind of the reasoning behind a lot of the cleaning requirements. But so that's what a lot of times we've seen. It's just people ask for the oxygen cleaning spec because it meets what they need, but it's not specifically for it's not written for hydrogen, but that's what we're seeing mostly right now.
Yeah. Okay. Awesome. Good. Well, I think that wraps up all the questions. Again, thank you so much, Tim. I really appreciate always very professional and knowledgeable. Thanks all for joining us today. Perfect timing, right on 10 o'clock. So nailed that. If there's any other questions, please feel free to reach out. Sam will be sending out a follow-up email to everybody that attended and signed up for the webinars. If anybody missed the previous webinars, reach out to Sam. He's able to share some of the links. And stay tuned for our next installment on that. So without everybody else, have a great, safe day, and look forward to talking to everybody soon.
Yep. Thanks, everyone. Thanks, CG. Thanks, everyone, for attending.
Thanks, guys.